Well, first of all, thanks for the kind introduction, and thanks to all of you for showing up this early in the morning. I know it's always a bit of a dare to give a talk right after the closing remarks, so I really appreciate you all coming here. I'm going to present, as said, work on bug search in binary software, which works cross-architecture. And I'm going to wait for the first slide to show up before I actually start the talk. OK, that works. As said, I'm going to present my work. It's, of course, not my work all alone. I've done it with some colleagues of mine, namely Berat Gamani, Robert Garlick, Christian Rosso, and my professor, Thorsten Holz. Unfortunately, Christian Rosso is not at the Ruhr University anymore. He switched to CISPA in Saarland, which I forgot to mention on the slide, so I should really mention it here. But all of them are actually in the audience, so if you happen to like this little piece of work, please make sure to tell them about it too. I'd really appreciate that. So, as said, cross-architecture bug search. If you ever feel a little bit lost in this talk, just remember that the key ingredient of it is a code similarity metric, which happens to work across CPU architectures. So if you ask yourself, well, why are we doing all this pre-processing stuff? It's to set up this key ingredient. They are slightly out of sync. We can probably get that fixed, right? OK, here we go. Key ingredient, code similarity metric. As said, if you are asking yourself why are you doing all this pre-processing, it's to set up this code similarity metric. If you don't know how we are looking for bugs again, it's with that code similarity metric. The basic workflow all over what we're doing is you show us a binary in either x86 or MIPS or ARM, unobfuscated, that is. You pinpoint us to the exact bug location, and then you give us another binary, and we will try to re-find the same or very similar bug in that binary, which may be compiled for another architecture. So, and the basic assumption with finding bugs with code similarity is that we know what a specific bug instance looks like. We try to find a piece of code which looks pretty similar to that. And, well, then it is likely to contain the same bug. And the reason for that is mainly because the reason for the code pieces being similar is that programmers are lazy. They will copy and paste code, and that means they will also copy and paste bugs. They may adapt them slightly to the situation, which is why we not only find the same bugs, but actually sometimes similar bugs. So, I'll start with not our work, but actually with somebody else's work, and that's for two reasons. First of all, because it really inspired what we did. Second of all, because I really like that overview graphic that they have, and that allows me to include it in my talk. So I'm talking about generalized vulnerability extrapolation using abstract syntax trees. It's a work by Fabian Yamaguchi et al., who's also in this room, as far as I know. And what they do is they analyze some source code, and the resulting abstract syntax tree is embedded into a vector space, and then they use the metric of this vector space to find similar code vectors, and if one of them happens to be known to be a bug, it's likely that the other ones may also be buggy. So what do we actually want to do? It's so their work for me mostly means that they abstract from bug classes, which may sometimes be hard to use in practice, actually. So what they do instead is they and we focus on single bug instances. Second of all, we want to focus on something like nearest neighbor search, actually. We don't do any fancy clustering or something like that, because what we actually just want to do is to find out if two pieces of code are similar to each other. Third, we want to do it not on source code, but on binary. And all that we do actually has sub-function granularity, because that is very important for bug search. If you think about it, if you know what a piece of code that has a bug looks like, it would be really cool to find that not only in the function that it's in, but actually also in another function. And that requires sub-function granularity. And last of all, we would like to focus more on the semantics and the structure of the code than on any symbolic or syntax information. So, and now it really starts with what we actually did. So we start off with an intermediate representation. As said, you give us an unobfuscated binary, be it x86 or ARM or MIPS. That's the architectures we support so far. And then we use the VEX intermediate representation, most known for the Walgrind memory checking framework. And that's IR is usually used for dynamic analysis, and we kind of misuse it for static analysis, which gives an own set of problems. But we also had to modify it heavily to abstract from some architecture-specific, let's call it idioms, so to say. And what we then do is we use basic blocks as our, let's say, single building block. And for each basic block, we try to accumulate the effect this basic block has on a specific register or memory location. So we accumulate all the little VEX IR instructions that have that specific register as target, and we got a big expression that explains what happens to this register or memory location in that basic block when you execute it. We pipe all that into Z3, and that is only to get a nice simple S expression out of it and to simplify it a little bit. So as you can see on the bottom, we start off with some assembly code. In this case, it's just something that reads off a memory location and increments a counter. And you can see that the assembly instructions are kind of different. They differ in the number of registers in there. Actually, x86 only has one instruction for doing both of those tasks. And the intermediate representation already looks kind of similar. So, but these complex assignment formulas, as we call them, are kind of hard to compare to each other. What you can usually do is you can use some unifying approach or something, which will tell you if they are equal or not. But that is really not what we want. We want some kind of scaling, gradual similarity measurement. So what we did was we sampled, which means that we generate a random input vector, execute the basic block on that input vector, which gives us an output vector. So, and we do that for a lot of inputs. And that really gives us some kind of point-wise semantics of this basic block. And now the reason why we do that is that similar basic blocks are kind of exposed to share these input-output vectors, these input-output pairs, and the more they share, the more similar they are. Now, from those assignment formulas, we have got a big set of I/O pairs, basically. And that isn't optimal either, because to compare them, you have to do something like whatever, the Jacquard index or something like that, which is pretty costly, actually. So we came up with another step, which is to use locally sensitive hashes. And those little things have a nice little property, which means that the similarity of the hashed object is actually represented by the hash. Which is not similar to cryptographic hashes, for example. And that allows us to save one hash per basic block instead of all the big list of input-output pairs. So that in the end, we can compare two basic blocks, actually find out how similar they are just by comparing this one little hash. So, and now that we've done that, we can actually go to how to find a bug with that. We start off with a bug signature. And in our case, a bug signature, which is just a catchy label we needed, is just a piece of code. It is not as abstracted as, for example, in network intrusion detection systems or something, where it's a glorified regex or something. It's just a piece of code. That's it. And a bug signature, in our sense, should contain the bug and a little bit of discriminatory context. But as said, it's just a piece of code. It's not structurally different from the target program we look for. We look in for the bug signature. So the next step is to find some starting points. We start off with a single basic block in the signature and try to find a good basic block level match in the target program, just to know where we have to start searching for a full signature spanning match. And that, as said, gives us some starting points. And a starting point is somewhat of a misleading term because it's actually a pair of points, one in the signature and one in the target program. You can see that in the big picture at the bottom. As said, we start with the signature and the target program, try to find some starting points. And the second part of that picture is actually done on this slide. So now we do have these starting points. And what we then do is some, what we call in the paper, basket broadening. And it just means that we explore the neighborhood around these two already matched blocks and broaden the match with the next best candidate we can find. So I'll try to explain it with the picture at the bottom. On the left, you always see the source program, the bug signature. On the right, you see the target program. And a big black arrow represents that two basic blocks are already matched. Now, at first, only the starting point pair is matched. And what I should mention next is that the similarity in that picture is represented by the number of edges. So the more similar the number of edges is, the more similar the basic blocks in that example should be. So as you can maybe see, there's two triangular blocks in the immediate neighborhood of the already matched block, and that is the next best match. So we fix that one. And in the picture in the middle, we get that next big black arrow. And we do that incrementally until we have got a full signature spanning match in the target program. This bested broadening is a greedy method, but it's locally optimal. So with all the neighboring nodes we have, we actually look for a full matching that spans all of them and try to find the optimum of that at each local point. There we go. So next we did some sanity checks. And what we did was we tried to match functions. Now a big disclaimer. Function matching is not our basic use case. As said, we want some sub-function granularity. But for that, you have to come up with some sub-function signatures. And we really don't have an automated way to do that. So the only way to convince you that it's not our clever choice of a signature that makes the match work is, well, just to use the whole function. So please keep that in mind. Function matching is not our full use case. We did not optimize for that. And actually, there would be some very simple improvements to increase our function matching score, so to say. And as said, our framework supports x86 and MIPS and ARM, so it's quite natural that you can compare x86 code to x86 code, which would be comparing code for multiple architectures. But it actually turns out that we can do a little bit more. We can compare code similarity from x86 to, let's say, MIPS. So we can do it cross CPU architecture, and it still works pretty well. It also works reasonably well for different compilers or different optimization levels. And as you might imagine, the less similar the code gets, the more it is transformed, like by, let's say, switching the OS, switching the compiler, switching the optimization level, or switching the CPU architecture, the less similar it will be. So naturally, the quality decreases somewhat. But it doesn't decrease as much as you maybe will think, and it doesn't decrease as much as to make the whole technique pointless. Well, on the bottom, you can see a little bit of that cross-architecture matching, where we plotted the rank of the true positive in like the ranking we computed before, with the summed up differences of the best match we had. We just sort them by the similarity, basically. And on the same architecture and even on cross-architecture, we can achieve pretty good matching rates at that point. On the bottom right, you can, well, maybe not see, but retrace with what I'm going to say. Our experiments regarding different compiler optimization levels. We took 3 compilers, compiled a piece of code with 4 different optimization levels. And the darker a pixel is, the better the match is. And you can probably see that for different compilers, the O0 optimization level looks pretty similar. Working on the same compiler works a little bit better than switching it. GCC on GCC works still pretty reasonable and stuff like that, all in that one little picture. Now that we've done the sanity stuff, let's go back to bug finding. Not that that's not sane or anything, but still, we go back to it. So these are just some examples. We have a few more in the paper. But first of all, we took the OpenSSL, the Heartbleed infamous one, and tried to find it cross-architecture. So you, let me remind you again, you show us the piece of buggy code in an x86 binary, and we are able to find it in an ARM binary or even in a MIPS router firmware. As you can see on the bottom left, where we always searched from ARM to another architecture or from MIPS to another architecture. x86 didn't fit on the slide. As you may or may not know, there's actually 2 vulnerable functions, 2 Heartbleed vulnerable functions at least. There may be more other vulnerabilities in OpenSSL. And those are the cases for TLS and DTLS. We used both of them as signatures, and so we also get like two matches, 2 match rankings for the 2 vulnerable functions. And as you can see in the table, they're ranked pretty much perfectly, even across architectures. We also did the same examples on BusyBox vulnerabilities and on the Circom backdoor, which we found in closed source router firmware, which is pretty cool. But the question that remains is, since all our algorithms do is give you a ranking, ranked by similarity, where the most similar matches are at the very top, even if you find a pretty good match, like the similarity values are pretty far apart from the next best hit, is it actually a true positive? And the sad answer is, we can't tell. Because all we do is find some local similarity. To find out if the piece of code is actually vulnerable, you have to do a lot more than that. You have to find out how to get to that position and how to fulfill all the necessary preconditions, the path conditions, to get to that point and to actually trigger that vulnerability. We can't do that at that point. And let me give you a nice example for that. It's patch code. A lot of patch code is actually just a piece of vulnerable code surrounded by a guard statement. And the guard statement basically says the path condition can never be met. But still, a localized code similarity metric that finds this piece in the middle as being similar is perfectly fine, right? That's its purpose. Still, this bug can never be vulnerable, which is a little bit problematic. But as said, for that special case of patch code, we tried to make a little improvement to that. You can just, given that you already know that the code can be patched and that you know the patch, use two signatures. So you once try to find a match for the patched signature, and if the function in question is more similar to the patched bug signature than to the unpatched one, it's likely that it's also patched. If it's the other way around, well, you're in luck. Maybe you find a vulnerability. But that is something that is really up for an expert to decide. It's just a hint in the right direction at this point. Here we go. So in summary, we work on binaries, no source code or symbols required. We have a very fine-grained sub-function granularity code similarity metric. And by using that code similarity metric with a bug signature as input, we can actually use that for bug search. And maybe the coolest thing, which is why it's at the top, we can do so across architectures. So from x86 to MIPS, from x86 or MIPS or ARM to any of the other architectures, that still works reasonably well. So in the end, we come up with cross-architecture bug search in binary software. And that concludes my talk, and I'd be delighted to answer all your questions.
So thanks. Yeah, Nick, you have time for a couple of questions?
Doesn't have to be about this. I'll answer anything.
Hey, Alex Kantman, Qualcomm. So it seems like sort of your work, you have to have a bug that you're looking for, so it's a targeted match. Have you looked at sort of more open-ended, basically bin diff kind of a thing? Here are two binaries, in different architectures. Show me similarities between them.
As said, function matching is not our thing, which is what bin diff usually does. And we really try to focus on bugs we already know about, but which aren't fixed yet. So we try to forget about all the new ones we don't know about yet. It would be cool to have those that we know about actually fixed. Our bug extrapolation capabilities are unfortunately less good than what you can achieve in source code. So we are more likely to find actually this, the same bug in another situation than actually find a different bug, so to say.
All right. Thanks.
You're welcome.
Hi, this is Fish from UCSB, and I think your work is very interesting. And the thing that is you can compare functions across architectures are pretty promising. One thing I want to ask is that for ARM, especially for ARM, they have a lot of conditional operations. Basically means a lot of instructions are conditional. Sometimes they are executed, sometimes they're not, based on context. And in our experiment, we see actually a lot of those. On ARM, you see many more basic blocks than other architectures because of those conditional operations. And how are you going to deal with that if you're comparing them based on basic blocks? And another question is that, I think I read your paper, and then you talk about how to pick the range of the values for sampling, and it's from -1000 to 1000. Is there any special meanings of that? And if not, what is a good way to pick the sampling ranges for relatives? Thank you.
Okay, I'll start with the second question, which concerns the range of the values we put into it. We experimented a little bit about it. We wanted to get like a pretty dense field, so we didn't want to have a lot of sparse values in it. But apart from that, we simply chose a number and went with it. And as it worked reasonably well, we kept it. That's basically it. There's no special meaning to it. To the first answer, we actually found out that MIPS has by far the most basic blocks. And that actually x86 and ARM are more similar than x86 to MIPS or ARM to MIPS code. So if you ever ask yourself, is ARM is still a RISC environment? Most likely not. Concerning the conditional instructions on ARM, we can just sample. So we can see a sampling value as an input to that binary condition. So if you just sample it a little bit, that conditionality will reflect in the output values. I hope that answers your questions.
Awesome, thanks.
You're welcome.
Hey, I'm Jan from UC Santa Barbara. From your paper, I gathered that part of your accuracy drop, aside from compile optimizations and so forth, is the cross-architecture part.
Sure, yeah.
And did you look into maybe grabbing samples of different source code, for example, compiling it for different architectures and doing an inner architecture bug search? Just single architecture, but since you have...
So I'll give you a partial answer and then ask you to rephrase what
Sure.
came after that, because in all our experiments, except the one for different optimization levels, we actually took code we found in the wild as it is. I don't know what compilers they used.
Right.
If they happen to use a similar one, all the better for us, but I really don't know. We haven't checked that. That given, please rephrase your question regarding the inner architecture thing. I didn't quite get that.
So I guess if you look at code in the wild and you look at MIPS router code, right, and you know some is vulnerable, and then you look at other MIPS routers to check against them, right, instead of looking for ARM routers, because there's plenty of, ARM code to check ARM code against.
Okay, yeah.
So I guess the question is, do you feel that the cross-architecture part is needed? Or is
So
it,
in
I agree, it's
theory,
very cool.
let's say you have the source code, right? And you have it usually compiled for x86, and you want to see if that specific bug in the source code is also in some MIPS router whatever code, right? What you could do is just compile the source code to MIPS and then check MIPS against MIPS. But you don't always have the source code, do you? So that simply doesn't work.
Cool.